Ready to record. Wonderful. Okay, so welcome back, everybody. We're ready for the second talk of today. I'm pleased to introduce Fabio Tanania. We'll talk about the isotropic, stable, motivic, homotopic category. Please, Fabio.
Okay, so first of all, thank you very much for the invitation to this seminar. I'm very glad to be here, to have this opportunity to give a talk here. And sorry again for this disruption and delay, but yeah. Okay, cool. So today we would like to talk about this isotropic, stable, motivic, homotopic category. So, well, in particular, I will briefly kind of present the construction and the main properties of this category, and then I will move to some structural results about it. In particular, I will explain what is the structure of the endomorphism of the unit object inside this category, and then maybe say a few words about the cellular part of this category. Okay, cool. So let me start first maybe by fixing a base field K, which is we work over flexible field. Right. By flexible field, I mean that it is a purely transcendental extension of countable infinite degree over another field. And we also assume that the characteristic of K is different from 2. Okay, so, well, then we start with...
Scusa Fabio, what is a keynotes?
It's just a field. So I'm just working over
another field. Okay, thank you.
K0 is a field, and then, just add infinitely many like transcendental generators. Okay, so then we can consider the usual stable motivic homotopic category over K. And I mean, the idea is that we want to localize this category in order to kill all anisotropic varieties. And this is essentially the idea that is at the base of the work by Vishik on isotropic motives. So we just apply it to the stable motivic homotopic category instead of the triangulated category of motives by Wygotsky. Right. So, okay, let's consider first an object Q here, which is the disjoint union of connected anisotropic varieties over K. Well, here by anisotropic, I mean that they don't have closed points of a degree. So no closed. Okay, so in particular, they don't have rational points. Right, so this is a sort of Mod2 version of an isotropic variety, but I mean, since we are working with characteristic different from 2, that's what we need. But I mean, in principle, one could define it for, I don't know, like Mod P version with, and one would require characteristic different from P. Okay, right, so we start with this object, which we can think of like as a variety with infinitely many components, and then we construct the check simplicial scheme associated to this variety, and this has on the n component is just the power to the n+1, and it has phase maps and the generalized maps, which are given by partial projections and partial diagonals. So essentially, this is the same thing as the construction in topology of the EG construction for a topological group, but while in topology we always have a contractibility of this EG object, then the situation in the motivic environment is a bit more complicated. In general, we do have something like this. So if I take the check simplicial scheme of X times Y, and this is a projection to Y, then this is a simplicial weak equivalence if and only if there are morphisms from Y to X. So if this smooth schemes, okay, maybe is different from the empty set. So in particular, we have that if Y is the spectrum of the base field, then this object is contractible if and only if X as a k-rational point. And for example, at least in our case, this is not the case because we are considering all these anisotropic varieties. So yeah, it doesn't have a k-rational point. So in particular, this object is not contractible. We can consider now in SHK, I mean, it's suspension spectrum, which I will denote in this way. Right, and then I can consider the morphism in SHK obtained from the projection from this check-simplification scheme to the base point. Right, so this is to the sphere spectrum. I can take the cone of this map, and I will denote by this the cone. And then I have this distinguished triangle in SHK. Then this spectrum, this Motivic spectrum, is called isotropic sphere spectrum. So the reason why it is called isotropic sphere spectrum is essentially this is the object that kills anisotropic varieties, and the reason is provided by this. So if, for example, we consider
sorry, Fabio, what is sigma plus infinity, this subscript plus?
Yes, well, I mean, it's just a notation for the suspension spectrum of this scheme. It's, I mean, I'm adding a point and then taking the infinite suspension, and so I get this.
Yeah, I know. You mean the suspension? You fix the sphere, say P1 or T, and then take the suspension. Right. I'm confused with the plus sign here.
I mean, usually, like, you have to have some pointed scheme, and so, I mean, I'm just adding this base point, essentially. This.
Okay, so this is just a suspension, the suspension.
Yes. I mean, if you don't like this.
Okay.
It's just suspension spectrum.
Yes.
Right. Okay, so if, right, okay, so if we start with an anisotropic variety P, then for sure there are morphisms from P to this Q, which is the union of all these connected anisotropic varieties. In particular, I get that this is a simplicial weak equivalence, this projection. So yeah, if I go to the stable category, then I have that chi prime smash this suspension of P, right, to the suspension of P. This is an isomorphism. And in particular, this means that chi smash the right, the suspension of P is trivial. So if we start with an anisotropic variety, then this smashing with this chi, with this spectrum here, trivializes all the suspension spectra of the anisotropic varieties. Okay. Right. So now we can consider a functor L from the usual stable Motivic homotopy category to itself, which is just defined an object by smashing with this isotropic sphere spectrum. And well, clearly on morphisms is just I mean, smashing with the identity on the isotropic sphere spectrum. And okay, so one can prove that this is a localization functor. And okay, yes, and this is essentially due to the fact that this chi is an idempotent in the stable Motivic homotopy category. And also we have we have such a thing, that morphism in the stable category from this is the same as X2. Okay, so we can consider the image of this, I mean, the image category of this functor, and I will denote this by SHK over K, and this is just by definition the full subcategory obtained by smashing with this isotropic sphere spectrum. Okay, and this is what I call isotropic stable motivic homotopic category. Okay, now this category has like very nice properties. In particular, it is both localizing and co-localizing, and it is also closed under taking sequential homotopy limits, for example, which I mean I will need it later, but I mean it has very nice properties, and one of the main goal would be to understand a bit better its structure. And okay, maybe just a remark on Vishik's category of isotropic motives. Essentially, that category is obtained in this way, by taking the motive of this isotropic sphere spectrum and tensoring with Pevotsky category of motives. Yeah. Okay. Well, once that we have this category, we can define isotropic stable motivic homotopic groups of a spectrum. And these are just maps from suspension of, let's see, chi to X. And I mean, since smashing with chi is a localization factor, this is just the same as usual stable motivic homotopic groups of chi-smash X. And we can also define isotropic motivic cohomology. Well, I mean, always with Zimot coefficients in this, in this talk. And this is the suspension of the Allenberg-MacLane spectrum with Zimot coefficients. So everything is essentially obtained by smashing with this isotropic sphere spectrum. Right. Now, yes.
Can I ask a question? Can you see the isotropic DM as a subcategory of isotropic SH?
Yes, I would say that is the well, it's the category of chi-smash H-Zimot modules inside SHK over K, I would say. I don't know if it's the subcategory, but
it looks like that's the DM, isotropic DM is a full subcategory, and there is a couple of adjoint functors from
for sure.
Isotropic by, I think, by localization theory, general machinery.
Yes. Yeah, there for sure there exists. I mean, Eilenberg-MacLane and motivic functor, the adjointness is kind of restricted to this subcategory, to these isotropic subcategories. So for sure you have something like this. But I mean, I think that if we want to interpret this isotropic category of motives inside, not inside, but related to this SHK, I think that SHK over K, I think it's just it should be the same as the category of chi smash H-Zimot modules, if I understand correct.
Yeah, sounds good. Thanks.
Okay. Yeah. Okay, so right. So one of the result of Vishik's paper essentially is the computation of the isotropic motivic homology of the point. So I will denote this isotropic motivic homology of the point in this way, and it's isomorphic to the exterior algebra over F2 generated by some arrays, and I mean these arrays are by degree minus 2 to the I plus 1 minus 2 to the I plus 1 plus 1. Okay, and essentially these generators are kind of determined by the action of the Milnor operations on them. We have this relation. Right. these QI are Milnor operations. Okay, now this localization, I mean this isotropic localization factor induces a morphism from the usual Motivic homology of K to this isotropic Motivic homology. And I want just to point out maybe with a small picture. So here, if we have the usual one by the result of Wygotsky, we know that we have here polynomial generator tau, and on the diagonal we have the Milnor K theory of K modulo 2. And here, I mean, just isomorphism given by multiplication by tau. And on the other side, we have this isotropic picture. And I mean, it's discrete. So it's like, it's a bunch of points. And these are in this third quadrant. So we have here 1, and then we have R0, and then R1, R01, etc., and points here. I just want to point out that by degree reasons, it is trivial everywhere, but in by degree 0, 0. So in particular, tau, it's sent to 0. Okay, so I mean, this is just to maybe to point out that this isotropic realization looks like kind of topological realization, but it's sort of perpendicular realization, because instead of sending tau to 1, it sends tau to 0. And I mean, so okay, so the picture is more similar to the, for example, to the study of C tau modules over complex numbers, for example. Okay. Right. So since I mean this essentially these results computes the endomorphism of the unit object in this category, triangulated category of isotropic motives, now essentially the main question would be to try to understand this endomorphism of the unit object inside this stable category. So the goal is to try to compute this, which again is the same of just usual Motivic homotopic groups of this isotropic sphere spectrum. Yeah, maybe that's the question. And the idea is, in order to get some information, we want to proceed by applying some isotropic version of the Motivic Adam spectral sequence. So since we will need it, first I want to say a few words about the Stirred algebra in this isotropic environment. So I will first define this isotropic Motivic Stirred algebra. Okay, well, this is just HTML2, and this goes to right. Now, a bit of structure of this Motivic stirred algebra. So, isotropic Motivic stirred algebra. So this is isomorphic as a module over the isotropic Motivic homology of the point to this tensor product over F2 over another algebra, this A0. Now we can describe this A0 as okay, so essentially it's an F2 algebra generated by stirred squares by degrees which are the same of the by degrees prescribed by the Motivic, usual Motivic stirred algebra. And then we mod out some isotropic Adam relations. Okay, now these isotropic Adam relations are obtained from the Motivic Adam relations by setting rho equals 0 and tau equals 0. So we don't get the usual topological Adam relations, but some kind of twisted version of it, I would say. Yes. Okay, but now I mean this is like a degraded algebra, and it's so if here we have like topological degree, and here we have Motivic weight, and this is the slope 2 line, then I mean this algebra is concentrated here, and we can consider the subalgebra which is just concentrated on this slope 2 line. And I will denote this subalgebra by G. Okay, so in particular, this subalgebra contains even squares and is generated by even squares. And yeah, what can be proven, which is interesting, is that it's isomorphic to the usual topological standard algebra, and the isomorphism is prescribed by this map. Yeah, okay. Okay, perfect. And then we can give description of this A0, which is just the tensor product over F2 of this subalgebra G concentrated on this slope line with this yeah, Milnor subalgebra. Yeah, maybe I will write here that M is just the exterior algebra generated by Milnor operations. Okay, so this gives a bit the structure of this isotropic Motivic stereoid algebra. There is a part which is given by the isotropic homology of the point, and then we have a part given by the topological stereoid algebra but spread on this slope to line, and then we have some part given by this yeah, Milnor subalgebra. Okay. Now we can proceed to construct this well, isotropic Adam spectral sequence is just the usual Adam spectral sequence, but everything is obtained by smashing with this isotropic sphere spectrum. So one starts with
Fabio, before you go on, there's a comment from Dan Isaacson in the chat.
Oh, okay. Yeah, sorry, I didn't see.
Might be easier to describe the isotropic duals in algebra. Can you comment on that, perhaps?
Right, the isotropic dual, yes, I think. Okay. So the isotropic dual should be so yeah, we take the so at least as an algebra, we take the isotropic homology of the point, and then we have some yes, some, I don't know, take generators, tau 0, tau 1, etc., and then C1, C2, etc. But then these tau I are exterior generators. So yes, should get something like this. So yeah.
Thanks.
Okay. So essentially, if we forget about this isotropic homology of the point, we get we get this exterior algebra in this tau I, and then a polynomial algebra in this xi. And I mean, this situation is similar to what happens in topology, but for prime p different from 2. And yeah, this is a sort of generalized, I would say, a stereoid algebra. Yeah, it kind of behaves as with prime p different from 2, the usual one, but is with prime 2 in our case. Okay. Right. Okay, maybe I will just go. Okay. Right. So yeah, we can consider the usual Adams tower. Right. Yeah, I will not maybe much more than this. Okay. Go on. And here we have some distinguished triangles in the stable Motivic homotopy category, and right, and then we smash everything with this isotropic sphere spectrum in order to get to this isotropic stable category. Right, and if we apply isotropic stable Motivic homotopy groups, then we get, as usual, a rolled exact couple, and then this induces like a spectral sequence. And with a bit of work, one can show that the E2 page of this spectral sequence is, as one would expect, the X where the isotropic Motivic stereoid algebra the isotropic Motivic homology of the point. Right. As this converges to the stable Motivic homotopy groups of the isotropic sphere spectrum, but actually to be precise, the HCMO2 nilpotent completion. Okay, so in order to get information on this object, we first want to study a bit this E2 page. And okay, so the first idea is to try to simplify it a bit, because as it appears, it's a bit complicated. So but maybe I will just say a few words on the simplification. We can consider some functors. So from G modules to A0 modules, and then to AK over K modules. Okay, so if we take a G module here, then I mean, since G is the quotient of A0 modulo the ideal generated by Milnor operations, we can consider just this tautological functor, and then we can go further by tensoring with A K over K over A0, right? With that, and I mean, this is isomorphic as a module over the isotropic Motivic homology of the point with this. Okay, so in particular, if we kind of focus on our situation, then we have, I mean, we can plug just, but maybe first of all, let me comment on this. So, I mean, this composition of two functors is exact, and so it induces morphisms. Right, this way to X over this. Right, so we have these homomorphisms, and if we suppose, I mean, if we assume that n prime is bounded above, which means essentially that X is P0 such that n prime PQ is trivial for P greater or equal than P0. Well, under this boundedness condition, then all these homomorphisms are isomorphisms for for all I, essentially. All I. Okay, and in particular, now we can focus on our particular situation, and we can plug n and then prime equal f2, and so we obtain this simplification for the for this E2 page. So STU. Right, this is by this result. Okay. Now recall that this G is bigraded, but is actually spread on this sloped line. So I mean, for T equal to 2U, we get just X SU A star F2 and then 0 otherwise. Okay, where A star is the usual topological stereoid algebra. So I mean, it can be expressed as just the usual E2 page of the Adams, classical Adams spectral series. Okay, and now if you look at differentials, the situation is pretty easy because, I mean, usual differentials of Motivic Adams type spectral sequence, they have 3 degrees r minus 1, 0. And so for r greater or equal than 2, we see that, yeah, by this structure of this E2 page, they all vanish. Yeah, because clearly, I mean, for r greater or equal than 2, then yeah, this increases, I mean, it changes while u always stays the same. And I mean, the only non-trivial groups of E2 page are for t equal to u. Right, and this means that this isotropic Adams spectral sequences collapses at the second page, and so it is strongly convergent. And I mean, in particular, we get the description of this. So this source prime, right? Of 2. This is x. 2 star prime minus star. Star prime. Right. Okay. F2. Okay. So we get this complete description of these homotopic groups of this isotropic sphere spectrum, and this is the same as the E2 page of the classical Adams spectral sequence. And I mean, this isomorphism is only additive, but since this object, this sky is an idempotent in the stable Motivic homotopy category, then I mean, it's also an infinity ring spectrum, and so these homotopy groups have kind of some extra structure. So in particular, it is a ring and it has some Toda brackets. And the idea is that with this Moss convergence theorem allows to kind of extend this isomorphism to an isomorphism preserving all this extra structure. So I want to point out that till now the situation is very similar to what happens for C-tau modules over complex numbers. So in particular, yeah, C-tau is like an infinity ring spectrum, and the Motivic homotopy groups of C-tau are identified with the E2 page of the classical Adams-Novikov spectral sequence. This situation for the isotropic realm is kind of the same, but instead with the stereoed algebra, so classical Adams spectral sequence. Okay, maybe I will okay, maybe I will just say a few words on what can be said about the cellular part of the stable Motivic homotopy this isotropic stable Motivic homotopy category. So we can focus on, so the idea is to focus on this SHK over K cell. So we just consider the localizing subcategory of the isotropic stable Motivic homotopy category generated by the isotropic sphere spectrum and suspensions. Right, and so the strategy is the same as the one used by Georg Wang Zhu to study the cellular part of C-tau modules, and actually we get a similar result. So this is isomorphic. Well, if we put some boundedness condition here, this is isomorphic to the derived category of A-star comodules. Right, so in particular, the cellular part of this isotropic stable Motivic homotopy category is algebraic, and it is the derived category of A-star comodules, where A-star is the dual of the topological stereoed algebra. And I mean, in order to achieve this result, one needs to first construct an isotropic version of the Adams-Novikov spectral sequence and work with the MBP, the Motivic Brown-Peterson spectrum. Well, yes. So yeah, essentially at the end one gets a kind of isotropic Adams-Novikov spectral sequence, and this has this shape. So if X and Y are cellular isotropic spectra, then yeah, there is this spectral sequence, which is X over the dual of the algebra G, which we said before, but I mean, this is just the topological zeroth algebra. And then here we have MVP star star X, MVP star Y, where MVP is the Motivic Brown-Peterson spectrum at the prime 2, and this converges to X. Right. Yeah, and by using, I mean, this spectral sequence and by studying first the category of MVP cellular spectra, then one is able to obtain this algebraic description of the cellular part of the isotropic stable Motivic homotopic category. Okay, cool. I don't know if I had more time, but I think it is enough, and this is what I wanted to say. So thank you for your attention.
Excellent. Thanks a lot, Fabio. Maybe you can tell us what this boundedness condition on isotropic SH is in this equivalent with this equivalence you got there.
Yes. I mean, since okay, so since everything is reduced to this MVP homology, so this boundedness condition, I mean, means that we are considering cellular spectra which have MVP homology, which is concentrated in some finite Chonovich of degrees. So yeah, I mean, so for example, we take MVP star star of this X, and yeah, so we the assumption on this boundedness that we can start with Chonovich of degree 0, which is just the slope to line, and then it means that yeah, there is some finite stripe in which this MVP homology is concentrated. This is the boundedness condition. So it's a sort of boundedness condition on the MVP homology of this isotropic cellular spectrum. And I mean, by the way, it can be removed, but yeah, what happens is that if you remove this this boundedness condition, then you obtain the stable stable category of A of yeah, comodules over the dual of the topological zeroth algebra. So yeah, something larger.
Okay, thanks. So we have time for more questions.
Fabio, can I have a question?
Sure.
In the very beginning, you assumed that your base field is the field of
yeah, flexible field.
Yeah, flexible. What is the reason behind this? Why is this field?
Right. Yes. So so essentially, I mean, the construction it's completely. I mean, it's available for every field. You don't need a flexible field to start with. The problem is that the computation of Vishik of the isotropic Motivic homology of the point is only available for flexible fields, because in order to obtain that yeah, that result, that the isotropic Motivic homology of the point is this exterior algebra over these generators, yeah, you need to have some kind of some control on finitely generated extension. And so flexible fields behave well in this matter, and so they allow to have this computation of the isotropic Motivic homology of the point. And since I mean everything I do after uses this in order to get the computation, for example, of the Motivic homotopic groups of the isotropic sphere spectrum, then we need this yeah, flexibility to start with in order to get this description.
Okay, ottimo.
Thank you.
Hey, can I ask a question to see if sort of I understand the kind of the big picture, how the computation goes? So
Yeah.
the steam rod algebra has these two parts, or at least the dual has these two parts. It has this exterior part and this polynomial part. And what you're saying is that it's the polynomial part that ends up contributing to the Adam Z2 page, and that the exterior part kind of disappears. And what happens is that it's because the coefficients are also exterior. But they're sort of canceling out each other out, and then all that's left is polynomial. Is that roughly correct?
Exactly, yes.
Okay, great. Thank you.
Yeah, absolutely. Because at the end, what happens is that what is used is that something like the isotropic Motivic homology of the point, which is this exterior algebra, is kind of dual to the Milnor subalgebra, and in particular it can be proved that it's an injective module over the Milnor subalgebra, and this allows the cancellation, as you were saying. So yeah.
Okay, last chance for a question, guys. There are no questions, Fabio, so everything's crystal clear, and thanks a lot for your talk.
Thank you very much for this opportunity. Thanks. And sorry again for every disruption. And
No problem. Thank you.
Thank you.